Okay, so in this video, we will consider the following family of linear systems. We've already written the linear system in its augmented matrix form. You can see k again is our parameter. As we vary k over all real numbers, we get an infinite family of linear systems. The question is the same as in the previous video. For which values of k will the system have no solution, a unique solution, or an infinite number of solutions? All we have to do is row reduce this augmented matrix and figure out which variables are sometimes leading, sometimes free, and when, if at all, there are possible inconsistencies, that being a row of zero coefficients and a non-zero constant. Let's row reduce. We already have a leading one in the leftmost column top row, so we'll kill the entries below it. So we'll do row 2 plus row 1 and row 3 minus 2 row 1. We can recopy the first row as we're not changing it. Negative 1 plus 1 is 0. K minus 1 plus 2 is k plus 1. K plus 1 plus minus 1 is k. Negative 1 plus 4, positive 3. Let's perform the second row operation. Row 3 minus 2, row 1. 2 minus 2 is 0. Negative k squared, negative k plus 4 minus 2 times 2 is minus 4, so this goes away. And we're left with negative k squared, negative k. We can factor in negative k, which will give us negative k times k plus 1. Negative k squared, negative k, check. Negative 11, negative 2 times negative 1 is plus 2. Negative 11 plus 2 is negative 9. And finally, 11 minus 2k minus 2 times 4 minus 8 gives us 3 minus 2k. So we have our first leading one. We've killed the entries below. We are now on the hunt for our second, and here the keyword will be potential leading one. Both entries here are potentially 0. If k is negative 1, they're both 0. If k is 0, this one is and not this one. So we can't just divide here by k plus 1 or by negative k plus 1 because both are potentially 0. And we can never divide by an expression that contains a value of k, as we have just seen, they are potentially 0. So all we'll do is we'll be satisfied with not a leading 1, but a potential leading 1. We'll keep the k plus 1 there as it is the simplest of the two, and we'll use it to kill this entry. Well, if you notice, all we can do is row 3 plus k row 2. If we do plus k times k plus 1 to negative k times k plus 1, the result is 0. This will kill this entry. Let's see what happens to our linear system if we do this. We can recopy the first two rows as we're not changing them. So we get 1, 2, negative 1, 4, 0, k plus 1, k and 3, 0, 0, negative 9 plus k times k is k squared minus 9, which we can factor as k minus 3, k plus 3. Difference of squares. K squared plus 3k minus k is 0, minus 9, k squared minus 9. 3 minus 2k plus k times 3, well 3k minus 2k is k, and so we're left with k plus 3. And now we've reached the bottom row of our matrix. And if you notice, we only have one leading 1 that is a lock. These other two values are potentially 0. So all they are right now are potential leading 1s. I'll circle them nonetheless, as this is the only potential leading 1 for y, and this is the only potential leading 1 for z. Well, there are always two possibilities. Either all variables are leading, or all variables are free. We always start with all leading variables, which means that k is not negative 1, as k plus 1 can't be 0. And k is not 3 or negative 3. And if you notice, if we choose k to be not negative 1, then this is not 0. Not negative 3, not 3, this is not 0. Whatever these values are, we could divide by their corresponding values and form a leading one for y and a leading one for z. Therefore, if k is anything but -1, -3, and 3, x, y, z are all leading variables. But if all variables are leading, this implies a unique solution. And now we're almost done. We figured that the system has a unique solution for every value of k other than possibly these 3 exceptions. Well, now we have no choice but to check each exceptional value of k one at a time. Let's start with k equals -1 and see what comes out. We get 0, -1 plus 1, 0, -1, 3. 0, 0, -1, -3, -4. -1 plus 3 is 2. 2 times -4, -8. -1 plus 3, +2. If you notice here, the matrix is not fully reduced. But let's look at these two rows. And let's consider now the corresponding equations. If you look at this equation, it says that -z is 3. And this equation says that -8z equals 2. Well, solve for z in both cases. Z is -3 is our first conclusion. If you multiply by -1/8, you get that z is, well, -2/8 is -1/4. Clearly, both are different, so it's impossible that z is at the same time -3 and -1/4, so the system is clearly inconsistent. Therefore, when k is -1, there is no solution. And that's it. You could have obtained the same conclusion if you had finished the row reduction. If you had multiplied row 2 by -1, and then killed the -8 by doing row 3 plus 8, row 2, and you would have had a row of 0 coefficients and a non-zero constant, which would also imply that the system is inconsistent. Either way is fine. Let's check our second exceptional value, k is -3. We get 1, 2, -1, 4. 0, -3 plus 1, -2, -3, 3, 0, 0, 0, 0. So let's see, x is leading. We could multiply row 2 by -1/2, have a leading one for y, so x and y are both leading. The third row says that 0 is equal to 0. The system is consistent, and since z is a free variable, it will become a parameter, which of course implies an infinite number of solutions. And that's it. Now to our final exceptional value of k, when k equals 3. Let's see what we get in this case. So we get the first row is the same, as there's no value of k in the first row. Then we'll get 0. K is 3 now, so we get 4, 3, 3, 0, 0, 0, 3 plus 3, 6. And now we have an obvious conclusion. Look at the bottom row. 0x plus 0y plus 0z, no matter what the choice of x, y, and z is equal to 0. This would have to equal 6. Well, 0 is clearly not equal to 6. The system has no solution, therefore it is inconsistent. No solution. And so we're done. We can finally write a proper conclusion. So what do we have? No solution, a unique solution, or an infinite number of solutions. Let's handle first unique solutions. K can take on any real value except for the three exceptional values, which are -1, -3, and 3, because for this case, the three variables are leading and implying a unique solution. We have no solution when k is -1 and +3. And we have an infinite number of solutions when k is -3. And this is our conclusion. So the original linear system has no solution, is inconsistent when k is -1 and 3. The system has an infinite number of solutions when k is -3. And for every other value of k, the linear system has a unique solution. And that's it.